and its environment. Okay, how the energy can be transferred as heat and work between the system and its environment. To answer these questions, we have the first law of thermodynamics. Okay, now let us consider a system. Here, please see the figure. We have a system which is a gas confined to a cylinder. We have the gas here, we have the piston here, and we have a movable piston. We have a movable piston here. The upward force of the piston is generated by putting a lot of electrodes. Okay, so I mean the upward force on the piston is actually the weight is generated by the weight of the electrode. This one. And at the bottom of the piston, we have a thermal reservoir for thermal energy. The thermal reservoir. Okay, and for this system, the gas will be able to do work on this piston. The gas is able to do work on this piston. The wall of the cylinder is very well insulated, so we enter what? A case of what? An open system or a closed system or an isolated system. What is it?
Isolated system.
Actually here, the system can still exchange the energy. You see, it can exchange the energy between the gas and the thermal reservoir. It can exchange the energy in the form of work, right? So here, this is a closed system, right? Not an isolated system. For an isolated system, we have no interaction, no heat interaction, no mass interaction. Here we have no mass interaction, but we have the energy interaction. So this is a closed system. Is that okay? And we can control the heat. Okay, we can control the heat temperature by adjusting the temperature. We can control, we can control the heat transfer by adjusting the temperature. Okay, so this is our system. We try to analyze this system to answer the question how the energy can be transferred as heat and work between the system and its environment. Yeah, I'm sorry here. Actually, it's a closed system, not an isolated system. Now, what we do is that we change the state of the system from an initial state to a final state. So we know that the initial state, a state is defined, right? Like I said, a state, it's defined by a set of properties. Here, our system, actually the gas. Yeah, the state, the initial state of the gas is defined by the Pi, Vi, and Ti. We change the system to the final state, then we have Pf, Vf, and Tf. Here we say here that we perform a thermodynamic process. Please remember the process. We already mentioned about this term. When we change the state of the system, actually we do a process, right? Here we change the system, actually the gas. The system here we consider is the gas. Yeah. We change it from an initial state to a final state. Hence, we perform a thermodynamic process. Okay? And the energy as heat here may be transferred into the system from the thermal reservoir or vice versa, right? If the system receives or gains heat, please remember, if the system gains heat, then the heat will have a positive sign. And that's why I put plus Q here. If the system loses heat, then the heat will have a negative sign. Please do not make any mistake. The work is also the same. The work can be done by the system, right? To raise the loaded piston, this one, okay? It can be loaded, so it will go up here, or you can lower it. When you load, you go up the piston, then we say that we have a positive work. This is the agreement, this is the convention. We have a positive work. And when we lower the piston, we have a negative work. So if the work is done by the system, then we have a positive work. If the work is done on the system, we have a negative work. Please take care of the sign. I'm trying to write down the work done by the system. Then we have a positive work. So here, if the work is done by the system, I mean the gas inside here, if the work is done by the system, then we know that the piston must be, must go up, right? Because this gas does work on the piston here, then the piston must go up. If the work is added to the system, we say that work done on the system, right? Here, for example, we have an external force added to the system. We say that there is a work done on the system, and we will have a negative heat. For another textbook, for example, if you go on the internet, there are some textbooks, they might give you another agreement, another convention. But I already showed you the textbook of Hadidé. And this we from now on we will use this agreement, this convention of sign. Okay, the work done on the system will take a negative sign. I'm sorry, negative sign. This is the work, not the heat. And the work done by the system will take a positive sign. Is it clear here? The work has a positive sign and negative sign. The heat also has a positive sign and negative sign. Okay. I'll try to remove what I have written for you to easier to follow. Now, sorry, wait a little bit. Okay. Now, if we remove a few electrodes, what will happen? Here, if we remove some of them here, then the gas will push the piston upward, right? This gas, if we remove some of them here, the gas will push the piston upward through a differential displacement. So I mean, when we say a differential displacement, ds here, we understand by a very tiny displacement. Okay, a very tiny displacement. Okay, so when we remove some of the electrodes, the gas will push the piston upward through a differential displacement with an upward force. I call it F, okay? Of course, it is in the form of a vector because when we consider the force, we need to consider also the direction of the force we already learned. Then we can assume that this force is constant during this very tiny displacement. Okay? Hence, we can calculate the force. Now, this force equal to the pressure of the gas times the phase area of the piston. This is the definition of a force. Okay, the pressure of the gas on the phase area of the piston will give you the force. I try to be slow here so you can follow me. Only if you can follow me. Now, this is the force. If we want to calculate, we want to estimate the differential work, so we call it the GW. If we want to calculate the differential work done by the gas during this displacement, then we can calculate using this formula. Here, the work, okay, is actually the product of F and ds. And if you replace the F, the force, by the product of the pressure and the area, what we just calculated in the previous slide, and then you transform a little bit of your formula, it will give you at the end the PdV. Okay? Yeah, because the area times the distance, the displacement, is actually the volume. Do you understand until here? dV is actually the differential change in the gas volume due to the piston's movement. Okay? The differential work done by the gas during this displacement is actually the product of the pressure and the differential change in the volume. Is it okay? Is it good? When we remove enough shot to allow the gas to change from an initial volume to a final volume, what will happen? We will have this one, right? We will have the total work. It's actually the sum of all the differential work. By saying differential work, we know that these are very small, very tiny works. And of course, the sum of them will make a total work for us. And the total work can be calculated using the integral, right? The integral from the initial volume to the final volume of PDV. Here you just replace the differential work by PDV. What is written in the previous slide here? The differential work can be replaced by the PDV. So then finally we have the work done by the gas. Yeah, the total work done by the gas will be calculated using this formula. And this is always true. This is always true. Okay. Do you have any questions until here? No? If not, I think we can continue. So this is the work done by the gas. Yeah, done by the gas when it changes from an initial volume to a final volume. Here, the meaning of this formula is that to evaluate the work, we need to know how pressure varies with volume for the actual process by which the system changes from state I to state F, okay, from initial state to final state. This is the meaning of this formula. Here, to express the work done by the gas, we can use a pressure volume diagram, or in short, in abbreviation, we just call it a PV diagram. It also has another name of volume pressure loop, okay? So the pressure volume diagram is used to describe the corresponding changes in volume and pressure in the system. Each dot in this diagram will represent a state of the gas. For example, you have the state 1 here, and it will have a pressure P1, a volume V1. If you have a dot number 2 here, it will have a pressure P2 and a volume V2. So each dot in the diagram will represent a state, okay? A state. And the work done by the gas, is actually the area under the process. In a PV diagram, a process is expressed as a line, a curve, and so on. Anything that relates to states, we have a process. And the area under the curve is the work done by the gas. Okay, this is the way how to read a PV diagram. How do we read a PV diagram? So here, once you understand, we can move further. The process, we have it. We can have a positive work. Okay, if the gas goes from the initial state here to the final state here. Why? Because we have a change in the volume. When we have a change in the volume, we have a work, right, done by the gas or on the gas. Here in this case, we have a work done by the gas because we see that the gas is expanding. The gas is expanding. The initial volume is smaller than the final volume. So we know that the gas is expanding. And when the gas is expanding, it will do a work. So we say that the work done by this system. That's why we have a positive work. Okay. You can see here, from the same initial state to the same final state, we can have a process that is like this, but we can go into different way. We can go like this or like this. Then what will change? The work will change. Right? The work will change. We say that the work is dependent on the process, or the work is a path dependent quantity. Work is a path dependent quantity. Okay, path dependent quantity. So we can have a negative work also if we have a process like this. Yeah. Here we go from F to I. We go from F to I. So this is the initial state. Here, this is the final state. We go from F to I. What do we have? We have a bigger volume from the initial state to a smaller volume from the final state. So then the gas is compressed. I mean that the gas is receiving an external force that forces it to compress. So in this case, we have a negative work. Do you agree with me? A negative work. Negative work. You can have a loop like this, and you still have a net work positive. Why? If I draw something here for you, how to draw it? If I draw something here from I to F, from I to F, I try to draw something. Then I draw. Okay, from I to F, we have this space, this area. Right? This is actually the work from the state I to state F. And from F to I, what do I have? From F to I have this one. I'm sorry, I have this one. Okay, and only this one. If I take the first one, the big one, minus the second one, I still have a network positive, which can be expressed as the area between the two curves here. Okay. Okay, do you understand until here? Good. If no question, let's move on. Here, to sum up, a system can be taken from the initial state to a given final state by an infinite number of processes. You can see infinite number of processes. Okay, I'm sorry, I tried to delete this one. And the work and the heat, both, they are path-dependent quantities. So if you change the process, the work might change and the heat also might change accordingly. The work and the heat are called path-dependent quantities because of this reason. However, there's a quantity that doesn't change, no matter what the process is. This is the quantity Q minus W. The heat minus the work is actually the same for their own processes. They found it experimentally. They found this one. Okay. The heat minus the work is always the same for all processes. Then this quantity must represent something. It must represent a change of some intrinsic property. Please remember, okay, the concept of intrinsic property. So Q minus W must represent a change in some intrinsic properties of the system. And we call this quantity internal energy. Yeah, internal energy. That's why we have the first law of the thermodynamics. So this is the first law. We have the change in the internal energy. Okay, will be equal to the heat added to the system minus the work done by the system. Please remember, okay? The change in the internal energy will be equal to the heat added to the system minus the work done by the system. Remember the sign. Here, the first law of thermodynamics says that the internal energy of a system tends to increase if energy is added as heat, and tends to decrease if energy is lost as work done by the system. Okay, as work done by the system. This is the first law. We will go to the four. I don't see that we have enough time. Actually, we have four special cases. We have the constant volume process, we have the adiabatic process, and we have cyclical process. Then we have a free expansion for the first law of thermodynamics. I think we can finish it in the next session. I try to take 15 minutes in the next session to finish it. And then we will try to do some exercise of the first law of thermodynamics. Okay, so to summarize for today, we have seen together some terminologies which are very important. Okay, when we say that, yeah, we talk about the process, you understand what is the process. When we say that, okay, we talk about the heat, we talk about the work, we should remember the sign. Yeah, a positive work is when the system does the work, or a work done by a system. A negative work, so the system will receive a work or the work done on the system. If the system receives or gains the heat, then we have a positive heat. If the system loses heat, then we have a negative heat, and so on. Okay, and then we also have to remember the formula of the first law of thermodynamics, and also the meaning of the first law. Is it okay for you? Now we have 3 more minutes. Do you have any inquiries that you want to ask, or do you want to share something? If, for example, something that is still not clear to you, no? So I suppose that you already understand. I suppose, firstly, you stay focused on my lesson. Then you already know what is the first law of thermodynamics, okay? You remember the sign. I will upload the slide to Moodle, okay? As I told you after the class. Yeah, I try to upload it. And then I may also upload the textbook